Oh,
Yes, good. Should I start over? Okay. So what's the smallest value of epsilon? Let's see, now I get myself off. Okay, what's the smallest value of epsilon that violates this primal constraint? What's the smallest value that violates this constraint? Well, you give me your smallest solution. You say 10 to the 50th. I say I can give you an even smaller one, 10 to the 60th, right? And so just to review, since this problem, it doesn't have a solution, we replace a minimization with an infimum. And so if we want to be technically correct, the problem that we're solving on the previous slide is an infimum problem where we're looking for the smallest in an infimum sense. However, because we're engineers and that level of exactness is not needed here necessarily, our problem is similar to this. For clarity, we're going to use the term min and smallest instead of the infimum notation in this presentation. You could also make an engineering argument that when we're talking about like the line limit on like a 2 gigawatt line, do you know that with infimum precision? Probably not. But okay, anyway, so don't worry about the infimum from this slide on.
So are we thinking about specific type of constraint violation or general, any constraint violation?
Any of them. We're considering the concoction of perturbations which would lead to network infeasibility. So that means your generation has limits, your line flows have limits. Therefore, does it mean we can't serve load because some stealthy combination of generation limits and line flow limits come together to prevent some feasible dispatch?
Because a targeted adversary can specifically target some
Yes.
constraints over the other.
Right, and you could think about a network that has, maybe it's a mesh network, but there's one kind of little island of the network and there's one weak transmission line connecting that island. You think, okay, just bring down that line, just increase load on the island until you bring down that line. Transmission grids are generally networked and they're meshed, right? But yeah, we could also consider more targeted approaches by maybe setting some of our perturbations to 0, for example, if we're sure that there's going to be no perturbation at that bus.
How does this relate to contingency analysis?
So you could have reserve constraints or security constraints that incorporate different like contingencies. And as long as in our framework, if you can represent those as linear inequality or equality constraints, we can incorporate it right into this framework. This framework has not yet been extended to DC-OPF, for example. But if you can have a contingency constraint that says like, the line overload in some contingency number 12 can't be greater than 37, if we can write that contingency using LP constraints, which we usually can for DC-OPF type contexts, then we could incorporate those. We don't incorporate them, but we could. Were you reviewer number 2 in our paper?
No, I don't think so.
So here's what we're going to do. We're going to take those LP constraints, and we're going to build this kind of Lagrange dual function, where P is our decision variable. This is our generator dispatch vector. Mu is our set of dual variable Lagrange multipliers. And now that we've built this Lagrange dual, we're going to exploit a well-known fact, which is when the primal will be infeasible when the dual is unbounded. So, okay, this is generally true. There might be some stipulations on it. But what we can say is that primal infeasibility is maybe kind of hard to suss out if we're trying to optimize over primal infeasibility. But hey, we can optimize over dual unboundedness because all we have to do is enforce dual unboundedness. So how do we enforce dual unboundedness of this little Lagrange dual problem? We need to do 2 things. We need kind of 2 conditions here. First, we have to zero out the primal. Meaning, if you think of this as like the max-min dance, you want to minimize what the primal can minimize over. You want to zero out what the primal can minimize over. So if mu transpose A is equal to 0, then this P variable has no effect, and the primal aspect of the problem falls away. And then what's left is we have mu transpose B delta plus C. And if we can show that mu transpose B delta plus C, if that thing just dips positive slightly, it means we can take mu, scale it up arbitrarily large, and we'll have dual unboundedness. So if you look at these 3 conditions together for long enough, you'll see that dual unboundedness will be kind of a result if if we satisfy these 2 conditions here.
So these are necessary, or what? They are necessary. There could be other ways in which unboundedness can arise.
Not that I know of. I think they're necessary. There could be some technical edge case that I'm missing.
Okay.
It's a good question. Okay, so now that we've made this observation, we can explicitly formulate this problem of finding the smallest adversarial attack to DC-OPF infeasibility. So what we're doing is we're minimizing over the size of the perturbation in norm 2 sense, subject to A transpose mu is 0, and mu transpose B delta plus C is non-negative. So this problem, it maybe looks cute, but it's a hard one to solve. So this is a parameterized version of Farkas lemma. If you think back to if you took optimization or convex optimization, Farkas lemma relates dual unboundedness with solvability of a system of LP equations. This problem is non-convex. Why is it non-convex? Because you're tuning both mu and delta, and so you have this bilinear interaction in this mu transpose B delta term. And this bilinearity leads to this non-convexity. And so you can kind of intuitively understand why it's non-convex. If this is your perturbation equals 0 base load operating point, and you're trying to find the smallest distance to infeasibility, well, here's one local solution that will give you, that will put you close to the constraint boundary, but it's not the smallest one. The smallest one is over here, right? And so because this program is non-convex, if you use a local solver to solve it, you might find this or you might find this, and you're not sure if it's a global solution unless you start branching down. And we'll see that in a minute. But
So
anyways,
this remark that it's parameterized version of Farkas's lemma help? Does it help?
does it help in terms of solvability?
Yeah, solution approach.
I don't think so. I mean, it is like if you want to use Farkas lemma to find the smallest adversarial attack, you're kind of led down this road, and you end up with something that looks like this. It's maybe a good way if someone has background in optimization. When I say Farkas lemma, it might ring a bell and allow them to understand what we're doing here a bit more easily. But just by saying the words Farkas lemma, there's no magic, I guess. Anyways, so this is a hard problem, but maybe like for small grids, like a 57 bus grid, maybe it's not that hard. But I want to show you very quickly that indeed it is hard. I can come back to the code. I'll go over to this. I can't see now I can see it. I'll run this kind of attack code. Let's see if this actually will work here. I'm going to start branching and bounding. I'm solving this minimization problem, and very quickly it finds an incumbent. This is the smallest adversarial attack it could find initially. You'll see the best bound is 0. What does that mean? It means it found an attack that's this small, and I happen to know that this is the globally smallest attack. But Gurobi has a lower bound. It said there could be an attack smaller. There could be, like, the best bound that we know right now is 0. Of course, if you can show that your system is primal feasible with no perturbation, you know that there's probably not an attack that small. But there could be some other stealthy attack somewhere between these two. And you think, okay, small system, 57 buses, a couple hundred constraints, probably wouldn't take so long to prove the bound on this one. Well, I SSH'd into the VAC earlier, which is the UVM supercomputer. This problem has been running for like 2 days. The bound is still at 0, or several days. So indeed, it's a hard problem. It looks like it maybe wouldn't be so hard, but Gurobi version 12 is kind of state-of-the-art spatial branch and bound. We give it this problem, and when we give it bigger problems, it can't budge this lower bound. We've tried different, focus parameters. We've tried adding different relaxation cuts, RLT cuts, McCormick cuts. I did an STP reformulation. The convex relaxation of this problem is very, very, very loose. And so you're always stuck with something near 0 or at 0 when you're at a sufficiently large system. So, okay, this has been running for a while. I'll let it keep running, but I don't have much hope that it will actually solve our problem. Okay, so all this to say, this is a hard problem. And this is kind of the start of the talk in the sense that when we wrote this down and tried to solve it, we realized we needed to do something more. And so now I'll tell you what we did more. So how can we close this gap? Right, this has been running for a while. Here's our best incumbent. Here's the largest known attack bound from Gurobi. It's stuck. What do we do? How do we close this gap? Hence the closing the gap subtitle. So I'm going to take you through kind of a series of ideas that get better. I'm going to start with a bad idea. Let's consider the primal constraint. So this is kind of our solvability condition. If I say delta is equal to 0, meaning there's no perturbations. And then I look at the amount of slack between 0 and each constraint. If there's non-zero slack, then I can just say, hey, I can loop over my constraints. We can kind of fix the generation variable, just let it be. And we can lower bound the smallest attack by finding the minimal perturbation that touches the constraint margin boundary for each constraint in the constraint set C. So this looks like this. You have, you grab the ith constraint, you set it equal to 0. And you say, what is the smallest perturbation that will drive that constraint right up to the feasibility boundary? Then you loop over all of your constraints, and you take the argmin of the 2 norm, and then you suddenly have, voila, a lower bound. This is pretty simple. Gurobi could actually just do this if it knew the structure of the primal. Gurobi does not know the structure of the primal because I gave it this non-convex dual form, and it struggles with. So here's a valid lower bound. This is not a good idea to do this, however, because what I've done here is I've implicitly assumed that only one generator responds to all load perturbations, the slack generator. This is a point we explain in the paper, but when I created this system of inequality constraints, I solved the power balance equation by basically choosing a slack generator and eliminating it from the variable set. It's kind of a technical detail. But anyways, assuming that one generator is picking up all the slack is kind of a bad idea. So what's something that maybe power grid engineers are a little more familiar with? That's distributed slack. You know, Suraj Dokle and others have these nice papers on using distributed slack. So to make our problem more general, we could embed a distributed slack policy into the control problem. So in this case, all of my generators, I can give them alpha. We call these like participation factors. And anytime there's a perturbation in a load, all of your generators are going to respond proportional to their participation factors in kind of picking up the slack, right? So however, this also is maybe not a great idea, even though this is something that we commonly do in power engineering, give all your generators a participation factor and then just let them respond according to those factors. Because first, generators, if the sum of the perturbations is 0, meaning if one load goes up by 1 and one load goes down by 1, there's no net change in the total load. And so none of your generators are actually going to change their set points. Also, what are these participation factors? How do you choose them? There are some chance-constrained optimization papers where they infer kind of data-driven participation factors based on historical ISO data. So you could do something like that, but it's not a good way to answer the question, is the system of equations feasible, given that we deviate from some data-driven strategy? Okay, so distributed slack, not the best idea. Here's another idea. We can go one step further, embed a fully general affine control policy into our feasibility problem. So now our generation response is going to be equal to some base dispatch value, nominal generator dispatch, plus G times delta. So G is a matrix. It represents a generator response matrix. Delta is our vector of perturbations, and it means that every generator's response will be a linear sum of these different perturbation values. The generation updates are now, quote, decided by this control policy. Like once we implement a control policy like this, perturbations drive how generation changes, right? So, you know, we have AP plus B delta C. We replace P with G delta plus P naught, our control policy. And then we end up with something like this, where now our LP inequalities, they're totally driven by the perturbation. And the generators will respond automatically to those perturbations. Yes.
Yeah, I'm wondering how this would work in practice. From my understanding,
it won't work in practice. Thank you. Are you reviewer number 3? So this policy, it's not an actual control policy. I'll tell you why. What is the interpretation of G? So this was Will's line in a response to the reviewer. The participation factors of each generator are different for each load in the network. That means if you think of the ISO New England grid, if you have a small load perturbation up in northern Maine, it means some generator down in southern Massachusetts will respond magically. No, you can't build something like that. And here's the point that we want to make, is that this policy is going to be, we're going to use it as a numerical crutch. It is not something we're proposing that you actually build and use to control a grid. This is not our deal here. We are coming up with a numerical control policy which can prove feasibility. Do not go and build this. Because you can't, and because you shouldn't, and because all the reviewers said the same thing. Please build this. So we clarified that in our revision.
So can I ask I'm sorry to distract you, but
No, that's
the
great.
original bilinear formulation, maybe you already thought about this, but you could perhaps also discretize the deltas and try to sort of look at some linearization resulting from that formulation.
That's a good idea. So in that case, you need to somehow bound the deltas. Maybe you need to know something about their upper and lower bounds, right? And then you can start thinking about chopping up the spraits, and then you start kind of branching and bounding, right? I mean, like, so that original problem, we tried to attack it, and we tried some convex relaxations and linearizations and things. We couldn't really crack it. And so we came up with like an alternative approach to prove the lower bound. If somebody in this room can be like, hey, there's clearly a better way to solve that original problem, that's great. And you should write that paper. It will build very nicely off of our code.
The delta could be having box constraints. Why do we have L2 norm?
So
usually delta is box constraint.
Right. So we're not putting an L2 norm constraint on the size of delta. We're measuring the size of delta using a squared 2 norm because that's nice mathematically to work with. You're right. You could put box constraints on delta. You could say that that aluminum smelting plant over there, it can't draw more than 500 megawatts. So
that may result in a simpler formulation to solve.
Yeah. So you could take the original. I don't want to go back to it.
Yes.
The original bi-level problem or this bilinear problem, and then you could add an extra set of constraints, which are box constraints on delta. It'd probably help. It'd probably guide Gurobi a little bit because right now delta is unconstrained. It's a good idea. Okay, now that we have embedded this control law, what we can do is we can find the smallest perturbation that leads to constraint infeasibility for each constraint. So I'm going to take this affine control law. I'm going to loop over all of my constraints. This is constraint I. I'm going to say, given this control law, which I don't know yet, but I've hypothesized it exists, what is the smallest set of perturbations which push my inequality constraint right up to the feasibility boundary? And if you look at this, you're minimizing over delta. And what this problem is, it's actually just constrained least squares. You have a sum of squares minimization, you have an LP equality constraint, there's a closed form solution. And the closed form solution that we derive looks something like this. I won't go through the steps of how we solve it, but this is like, standard calculus linear algebra type tricks. So what do we want to do? We want to choose the control policy, which maximizes the smallest perturbation across the entire constraint set C. So I'm going to loop over my constraints, find the one that's kind of the limiting reagent, the one that causes infeasibility first. And I'm going to try and maximize over the minimum, meaning I'm going to choose my control policy parameters such that the smallest distance to infeasibility is maximized. Okay, so just a little bit of math here. So here is my max-min problem. I then take this, this laser's not working. I take this kind of 2 norm squared perturbation. I say, hey, I have a least squares solution that I drove on the previous page. And I replace that squared 2 norm with this closed form expression. And then I use, the so-called epigraph trick to get rid of the minimization. I introduce some lower bounding variable t, and I'm pushing up on t, and I'm trying to find the control policy parameters which maximize t. Okay, so now we have a new problem, an entirely new problem. This problem, it's non-convex as well. Another non-convex problem. We don't actually go and solve this. You have to reformulate it to solve it for numerical reasons. We do that in the paper. It's not only non-convex, it's also very ugly because G is a matrix that's dense in variables, meaning it's m by n, where n is the number of generators, n is the number of loads. So it can be a very big matrix. It's non-convex. It's also somewhat numerically intractable for very large systems. Future work will hopefully make it a bit more tractable. But so here's our problem. So this is, now that we have this, we can use it to find a lower bound on the attack radius. So the key lemma that we then exploit is there's no attack smaller than the defense radius T star. So any solution to this, any feasible solution will give us something called the defense radius. It means there's no adversarial attack within this defense radius, which could generate infeasibility. And the proof is basically the identified control policy guarantees non-zero constraint margin for all perturbations smaller than or equal to T star. And so that's helpful. T star, we call this the defense radius. And so, for example, our program on the previous slide, it was non-convex. However, any feasible solution will give me a guaranteed region wherein which no adversarial attacks can exist. They can't be there. We proved it. So that's great. What we're going to do now is we're going to define delta as the set of all feasible perturbations bounded by the adversarial attack. So this delta, capital delta, is going to be this red dashed ball here. And delta is the set of perturbations such that all perturbations within that set are smaller than the adversarial attack. And what that means is, by definition, all perturbations in this kind of red ball, they have a feasible solution. For all perturbations within delta, there exists a feasible dispatch which will allow you to feasibly solve your DC-OPF equations. Now, our conjecture, the thing we wondered about now after we constructed this control policy, is this. Given an optimal control policy, can its defense radius be as large as the smallest adversarial attack? Can the defenders meet the attackers head on? Is there zero gap between the two of them? And so here's our conjecture. There exists P naught and G, these are control policy parameters, such that we have a solvability condition for all perturbations within delta. Okay, so this was a conjecture. This summer, wrote down something like this. I was pondering it, had some ideas. I thought it'd be easy to solve, and I realized it was not easy to solve, not easy to prove. And so what did I do? I said, hey, we have a new postdoc in town, Wheeler. Will Wheeler. He arrived recently from UIUC. I thought, he's at least 30% smarter than I am. So I went in his room and I wrote down the conjecture. And then he came to me days later and he had basically proved it. And so what we're going to do now is Will is going to present his nice thoughts on the matter. And then we'll transition back to.
So in control problems, having some structure on capital G sometimes helps. For example, lower diagonal and things like that. Does it make a difference?
It probably would, but we're dealing with the PTDF matrix. It's kind of dense shift factor matrix. And then we have not exploited sparsity. There's probably a clever way that someone from MIT could exploit sparsity that we did not do, but it's a good point.
Yeah, so Sam posed this question and said that I solved it. And what I said is, I don't know how to solve that question, but if we make the question a little bit simpler, we make some kind of approximation on the question, then we can do something. So this slide, I kind of just repeated the story. At the top is the constraint that you've been looking at. The AP plus B delta plus C is less than or equal to 0. Those are all the constraints. And so I call the delta, I call it feasible if there's a solution P. And then Sam defined the smallest adversarial attack, delta star, and the set delta, that is all the capital delta, all perturbations that are smaller than the smallest adversarial attack. So anything in that set delta is feasible. And then this linear control policy. And again, the point of the control policy is not to implement it, but it's that we want to, as well as possible, we want to find a lower bound to these adversarial attacks. And we know that if there exists a control policy that creates a certain defense radius, then there can't be an attack. Regardless of whether we implement it, we know something about the size of these attacks. Okay, so the conjecture that Sam posed is there's a control policy that yields a feasible solution P for all delta in this set delta. And then this equation again, if you plug in the control policy, the constraints turn into this equation. So my way of thinking about this constraint problem, we got the P's and we have the deltas. And if there's a solution, I can think of the P's and deltas as sort of like one combined variable. So there's some space, and these are all linear inequalities. So the solution space in the combined P delta will be some convex region bounded by linear cuts. And so I have my little diagram of that here where I just like one-dimensional delta, one-dimensional P, and I can make a little linear bounded region. And the first approach of let's just kind of pick an operating point and see what the bounds are is the left picture, where you say, I choose P0 as the operating point. Now let me look at, for that P, what deltas are feasible. And you get some subset of the total deltas, where the total deltas, these vertical lines are like all the deltas that correspond to a point in that square region. And if you choose a better control policy, which is this linear slice through it, you can, in this case, you can get the whole region because delta is just one dimensional. So this is my way of wrapping my head around the problem. Okay, and then I thought, wouldn't it be cool if I had a higher dimensional image for this? And I made one. So this is the example with the two-dimensional delta space and a one-dimensional P. You have this region that's got unfeasible solutions, and you're interested in the delta space, the projection of that. What are all the points delta that have some set of feasible P? And then I want my linear control policy is taking a linear slice through this. And that's sort of mapping, every delta maps to a P, maps to a solution. And now the conjecture is saying, can I always find a slice through this region that completely covers the shadow in delta? And I don't think that's generally possible. Like you think of some examples, you're like, doesn't seem possible. In this case, the slice that I drew, you can see it doesn't quite cover the whole space. So what do we do? I say let's not consider the general case of I want all the deltas within the set delta to be covered, but if it's possible to enclose that ball delta inside of a simplex, I'll consider that problem. Now, so what I mean by simplex is take in n dimensions, take n+1 points and take the convex hull. So that's in 2 dimensions, that's a triangle. In 3 dimensions, that's a tetrahedron. Those kinds of shapes where it has a set of vertices and every vertex is connected to every other vertex. So I'm going to consider that sort of shape. And there's a fact about simplexes that is that any point in the interior is a convex combination of the vertices. And that convex combination is unique. If you pick a point, there's a unique combination of weights. If you enforce that the weights are greater than 0, a unique combination of those weights that represents that point as a linear combination of the vertices, and those weights will sum to 1. Okay, so then the theorem that we can state is that there is a control policy, G and P0, that satisfies our constraints for all delta in the simplex, if and only if the values, the vertices of the simplex are all feasible. So again, we're talking about, we want to show that all the deltas are feasible in delta. And so then this image at the bottom is sort of showing the ball delta and like an example of that being contained within a simplex. And if you can do that and the vertices of the simplex are all feasible, then you can show that all the points inside that simplex are feasible.
What's the interpretation of this delta J in terms of the original adversarial attack problem? So
I'm sorry, say that again?
So you had this original adversarial attack problem, right? Is there any interpretation of this vertices delta J's in terms of the actual adversarial attacks that would be rendering the problem infeasible?
Yeah, so I use delta because these are perturbations. It's the same type of thing. These are perturbations to the loads. And some perturbations are feasible if I can solve the problem with that perturbation. It's infeasible if I can't. And so I'm considering that there's some set of perturbations that are feasible, that you can solve those constraints.
But you link this back to the adversarial problem soon, I assume.
Right. So the goal here is to compute the defense radius, saying that within this radius, I know that there's no adversarial attack. And so the control policy was, the point of the control policy was to say, like, can we find the tight lower bound? Can we
Okay.
say this is the smallest adversarial attack? And if you solve that conjecture, then that says like you'll be able to build that control radius all the way out to your smallest attack.
Thank you.
So what we did here is say we might not be able to do that, but in the case where you can enclose that ball in a simplex, we can guarantee that you're going to get that exact lower bound. Did you take out my math slide?
Oops.
I put the math on there, but I think it probably isn't that interesting anyway. So
I didn't intend to, but it goes from 3 to 5, so I must have.
so I'll just sort of say conceptually what the step is. So these, you take this this set of points delta, they can be anything.
Pull it up.
No, I think it'll just be easier to.
Sorry.
So it rests on the fact that these weights W are unique. And so I have this image here which doesn't explain itself, but the idea is the axes are different weights. So like maybe there's 3 weights for the 3 different deltas, which means I'm in 2 dimensions. And the sum of the W's is 1. And so that's the plane that I drew across those axes. And basically I've taken I've got n dimensions and n+1 points. But if I add 1 extra dimension, like I did taking this triangle and adding 1 dimension, now I've got n+1 by n+1. And because of this uniqueness of the weights, that matrix is invertible. And that means that actually, if I just, for each delta, we said they're feasible. So for each of those feasible deltas, I'll find a solution P. So hypothetically, I don't actually have to do this, but I'm just for the sake of proof. I could find that, and I can take that collection of P's and make a matrix. And now this collection of deltas, I said I can make an invertible matrix out of it. And it turns out that if I just multiply this set of P's by the inverse of the deltas, the matrix that I get out is the control policy. It is the G in the P0. And so it basically proves that this control policy is the one that satisfies this condition.
The simplex is in how many dimensions? Simplex is n+1.
The simplex, so it's n+1 points in n dimensions. So if delta is the number of loads that get perturbed, and so if that number is n, then to construct a simplex, I need n+1 points. So
And the invertible matrix is n+1 times n. So it's n plus. Okay.
Well, it's 1150. I think we should keep that.
yeah. So that was my non-written explanation of the proof. And then the only thing left is sort of saying, I proved it for that case. Obviously, that won't always apply. So for example, in this third picture, you see a simplex that doesn't enclose the red ball, but it encloses a smaller green ball. And so we can, be guaranteed that there's a defense radius up to that point, but there may still be a gap between that and the smallest attack.
Thank you, Will. So just to summarize, we have this Farkas lemma thing, which can find local adversarial attacks, but it's hard to prove global optimality. So this is like what Gurobi found as an incumbent, but we had a hard time proving the 0 side. And now we have this new control policy, which can defend against all attacks smaller than T star, but we don't know if T star is conservative because of this question about simplices and balls and things. And also it might be hard to prove the upper bound, which we find in our tests. However, if we show that T star is equal to, delta tilde transpose delta tilde, what we found is the globally optimal attack. So it doesn't mean if Gurobi can't improve from the 0 gap, and if we're still stuck at an infinity up here in terms of the size of the control radius, if we show that T star is equal to delta tilde, this thing here, then we've proven that we found the globally smallest attack. So a few points about test results. I guess I'll kind of skip this because we're out of time. We solved all this in Jump, Gurobi, IP-opt, etc. for hot starting. You can see our paper. All of the big computations were run on the Vermont Advanced Computing Center, blah, blah, blah. Here's some results. First, on a 5-bus system, when we initialized the system, we had an attack incumbent right here, and we also had a control radius incumbent, and they happened to match at initialization. So while we couldn't prove an lower bound on the attack, and we couldn't prove an upper bound on the control radius within, let's say, 100 seconds, it didn't matter because we knew that we had a globally optimal solution here. And the analogy here is that T star was equal to the smallest adversarial attack. So that's for 5-bus system. And then we have results on some bigger systems. So very quickly, we were able to show, so we ran like 30 minutes of branch and bound for some of these smaller systems. For a 5-bus, 14-bus, 24-bus, 30-bus, 57-bus, 60-bus, we were able to show that even though the attack lower bound was stuck at 0 and the upper bound on the defense radius was stuck very large, we showed that the incumbents matched on the defense radius and the adversarial attacks. And so it means that we had a globally optimal solution very quickly. There's one, the bigger case, and this approaches the limits of the tractability of the approach right now. There was a gap between the smallest known attack and the largest known defense radius that we could find. We ran 3 different reformulations. So we knew that we actually could find the globally optimal defense radius given our affine control policy. We ran a bunch of different reformulations of this network to try and close this gap, but we could never improve from a very small lower bound. And so we truly don't know if there's a gap between our optimal defense radius and the globally smallest attack, or if Gurobi just couldn't find a very sneaky attack. Maybe we'll let this run for days and weeks and see if we can find that sneaky attack, but right now there's a gap on this biggest system.
So in all these experiments, Gurobi had branch and bound the good attack just in the first iteration, or you took more time?
Yeah, we took a series of steps we initialized Gurobi with some hot starts of IP-opt, and we fed it an incumbent that looked good. And usually that incumbent was actually like right on the money.
There's no reason on why it is the incumbent itself is a good attack in general.
No, because you can find lots of local solutions. If you run IP-opt a bunch of times, you'll find a bunch of solutions to the local adversarial attack. And here's just one little intuitive example on the 57-bus grid that you all were operating earlier. Here's what the smallest adversarial attack looked like that brought down the network. So I'm plotting load buses and the change in load as a % of total system load. And what you see is like 1% increase in load, 1% increase in load, a small decrease in load, etc. This is a pretty sneaky attack. The system operator couldn't just look at the grid and say, ooh, if I tinker and tune all of these little loads just slightly, we find this attack that brings down the network. But lo and behold, we could prove this was the globally smallest attack. Is this new? I'll just briefly mention the 4 horsemen of the DC-OPF apocalypse. We have chance-constrained OPF, robust OPF, convex restrictions, and then OPF adversarial attacks. In our paper, we go through a pretty extensive lit review in terms of comparing what we've done here, which we think is pretty different from what these other methods look at. And because of time, I won't go into it. But basically, our work finds the smallest load perturbation, which renders DC-OPF infeasible. We could not find any other paper that ever really looked at that, either because it's a useless problem or it's because of a hard problem. We think this is a hard problem because it is actually pretty hard to solve. With that conclusion, we used Farkas' lemma and we formulated an adversarial attack problem to find the smallest distance to infeasibility. Turns out this is a hard problem. It's hard to prove optimality of this formulation. To lower bound the problem, we designed a tunable affine control policy, which provides a guaranteed defense radius where there can exist no adversarial attack. Under certain assumptions, the simplex assumptions, we prove that the distance between the attack and the control policy squeeze towards a common global solution with 0 gap, even if you can't prove the bounds of either of the models independent. Future work will address scalability, scaling this approach up, alternative control strategies. You could do piecewise linear, quadratic, etc. We used affine because it has nice least square solutions. And then extending this to like nonlinear network contexts we think would be pretty interesting. All right, I know we're a little over, but thank you for your attention. We appreciate it.
Thank you very much. Very interesting talk from Professor Samuel Chevalier. Any question?
Thanks for the nice talk. So, yeah, I was curious, like, I think it's a good reminder that the global optimization, even for the small problem, is a very difficult problem, especially if you're doing the spatial branching bounding.
Yeah.
I mean, like, I wonder if you have like thought about kind of the different way to formulate the problem. For example, you want to find the delta that gives you the maximal infeasibility, given some constraint on delta. I think like one other way to think about the problem is in that way, because you can like scale this size of this delta,
Yeah.
allowed delta set.
Yeah.
That's just one dimensional variable. And you can try to identify the point where it gets into infeasibility. And then like that's gonna be your smallest attack. And if you formulate the problem in that way, probably you can try to minimize, minimize the maximum infeasibility. No, minimize the delta that gives you the.
We did this.
Oh,
We actually just, so there are multiple ways of formulating this problem.
Yep,
Another way to formulate it is a bi-level approach.
Yep,
So this is direct Farkas lemma. You're describing a bi-level approach where basically you still minimize over the size of the perturbation, and then you maximize over constraint violation, and you force at least one of the constraints to be non-negative.
Yep.
And in that case, when you end up with bi-level, it's a min-max. When you reformulate bi-level, you actually end up with something that looks like this. It has some slightly different constraints, and you end up with some additional primal variables. But you can do what you're proposing, and actually that is one of the formulations that we tested to close the gap, assuming that we're talking about the same thing.
But if you're doing the min max, if you, for example, like replace the inner problem into KKT condition,
Yeah,
then
that's what we did.
Then like did Gurobi handle?
It still had a hard time.
I see.
Because when you replace with KKT conditions, you still get a mu transpose times some set of inequalities. And then inside of one of those inequalities is a perturbation variable. So you still get bilinear interaction.
Yeah, but
between the
can
KKT
you do the
over-
integer
We did not try MIP. We did
That's
not.
what I mean. If you do KKT and do some integer, it
Yeah.
should be able to handle.
Ah, good. Okay, so let's explore this because that might be something that unlocks better scalability here.
Yeah, probably you cannot get away from the non-convexity, but
Right.
probably Gurobi can handle
Yeah.
the integer branching bounding much.
So there also is a degree of freedom here. Like any mu value that satisfies these equations, you can scale mu. And so like you can add like the sum of mu is equal to 1. There's different ways of regularizing this problem. We didn't branch and bound over integer, forcing individual constraints to go. There's probably some way to do this. However, I feel like it's not just one constraint that will be violated. I think there's going to be two at a time. But yeah, it's worth thinking about this more if you have good ideas about using integers to make them. Because like if we could have solved this problem, we would have just written this as a short paper and be done. I don't have the rest of it, but the rest of it was fun too.
I want to follow up with that question. So can you go back maybe to page 5 for at the original formulation? I'm thinking,
This one?
yes, I'm thinking about another way. So for example, if I give you, so you're trying to search the kind of Swiss hole such that if the delta is smaller, is within that board, then
Yeah.
everything is visible, right?
That is a way to reformulate,
Yeah,
to formulate kind of a robust
Yes,
optimization.
yes. And then
You can do that.
So if I give you this number, you can validate it, right? There's a max min, and you can find actually it's the SOCP because you have all this linear kind of objective and linear constraint. So you can use a bisection of that bound. So for example, I search 0, and then that should be feasible, and then I test 1, and it's infeasible, and then test 0.5 at the middle point, and then it's feasible, then I test 0.5 to 1.
Yeah.
So you kind of have so this log n algorithm time, and then each run you are running a kind of a SOCP. In some way, you kind of, I think it's a more efficient way than MILP.
Yeah, that's very interesting. I'd love to learn more. So we looked
Actually,
at
I have a similar paper like
Oh,
this,
good.
but
Okay.
like I'm using this bisection to search the step size. Similar is one dimension. That's one dimension because this problem has a very special structure because if the solutions exist, then they should be unique. So that's the really special kind of things.
Okay, I will say that this minimization, this objective function, when we go and we formulate the vanilla version of the problem, we drop cost objective because we don't care anymore.
Yeah.
So yes, there is unique DC-OPF solution, but
But
this
it's
is the
unique,
more.
so, and there's one dimension, so you can use bisection search. That should be
Yeah.
very sufficient in that. And then also you do not need to solve
However,
this.
our delta is a vector.
It's vector is okay.
Yeah.
Oh, it's a vector, okay.
So you're looking for these stealthy attacks. You know that plot I showed at the end where
No.
loads all perturbed?
Delta is vector, but the bound is one dimension.
I see.
The bound, you just
So-
search the bound.
So there's a number of robust optimization papers where basically they come up with some box constraints and they try to prove that there exists a feasible solution everywhere in the box or something.
Yeah, just like.
That problem does not solve the minimal
Yes,
attack.
yes.
You
So
then
you
use
should
the
add
bisection
a
technique, yeah.
bisection search by that as
Mhm.
well. So it's
Yeah.
kind of like two steps. Step one,
Yeah,
you have a bisection on the kind of the radio you want to search, and then
Yeah.
the second one is the robust. Actually, you do not need to solve the whole robust. You just
Yeah.
need to check it's feasible, and
Yeah,
then
and
you can return back.
it would be interesting to see like, if you use the bisection method. So like Gurobi found without hot starting, oh geez.
That's really good resolving to check.
Yeah, so Gurobi actually found the optimal adversarial attack instantly. There's no hot starting here. And the question is, bisection would maybe take a little bit longer, maybe find something like this, but bisection you could prove it's
Bisection is
optimal.
outside optimization.
Sure.
Yeah. Maybe we can talk more like.
Yeah, that'd be great. We'd love to see your paper.
So a question from the online participants.
Yeah.
Yifo, please unmute yourself and. pose a
Yes,
question.
thanks for the presentation. I just want to ask the physical meaning of attacking size. Like you draw a circle for describe the size, like how you normalize different contingency and load uncertainty into this kind of size.
Will, do you want to answer this? Because you had some thoughts about this.
Oh, this is about choosing the
Size of the attack.
norm?
Yeah. Or
Yeah, so before you have a slides which show the size of the attack size.
yeah. So we in this paper we use the 2 norm, and like that would mean like all attacks are equally likely, and we didn't put any restrictions on which loads could increase by how much. You could add constraints on which loads could perturb or not, or use like some covariance matrix that weights these attack perturbations proportional to some distributional knowledge you might have. But we didn't look at anything like this. We just said, given all of the loads in the networks, any load where there's non-zero load, it can perturb. We did not put a box constraint on it, and we didn't add any sort of a distribution. We just assumed that, I guess that's non-informative distribution or something. Yeah. Does that help answer the question?
Yes, thank you.
In that sense, how could you come out with the things that when you test on the system by compare the ratios for the colorful one?
You mean this map that we showed at the end?
Yes.
So this system, we in the 57 bus network, there's some number of loads that have non-zero load, and we allowed all of those loads to vary very freely from their base point, meaning that there is some nominal value of load, and they can fluctuate up or down, and some of them went up, some of them went down.
Yes. So this is just one of the cases. Or
Yeah.
it's the
Yep, this is one of them, and then the other ones we tested were in this table here.
as long as the total perturbation will stay inside that
Right, yeah, there exists no perturbation smaller than 6.29 within an L2 norm circle that could bring down the 5-bus grid. We have a guaranteed defense radius within that circle.
So in theoretically, when this kind of perturbation happens in one node or it happens in a distributed way in different nodes, theoretically, your methods have no difference on the defense radius.
Yeah, you could, oh, that's true. Yeah, that's interesting. Yeah, I mean, the defensive radius will grow if you assume you add constraints, which say only nodes with solar power can have perturbations or something. So this probably represents a worst case, because generally, again, many loads are fixed and probably aren't going to deviate by much. but maybe your illuminating smelting plant is gonna go off, or maybe you're in Virginia and all your data centers pop offline because like voltage or trip. Yeah.
So last question from Olu.
Okay, so first common prop. So I think you are assuming a very sophisticated actor here.
We didn't, so we tried not to assume that the attacker, we tried not to anthropomorphize the attacker. We said it could be renewable energy fluctuation, could be coordinated DER control from aggregators. It could be just load certainty or load forecast uncertainty. And so we wanted to be agnostic to the source of the attack. We said, but what is the smallest attack?
I think it's reasonable to take that interpretation because, you know, if people have models of probabilities of different things, you could argue that like, you're not going to find the smallest one. It's not probable. But if someone was actively trying to find the smallest one, then they would be incentivized to do some optimization to find it. And we're trying to also find it to defend against
So
it.
doing their job, right?
Okay, let's call it a day and thank you everybody.